Okay, so welcome to the fourth lecture. This will be on the column. So hopefully all of you know that all of the lectures and experiments tentatively for here on out are going to be done online. So not ideal, but we're going to make do here. So today's lecture 4 for the column. Then our next lecture will be on the Charpy impact. And then the last lecture will be on double shear. So, like I do pretty often, I'm going to first kind of give you an idea of what we're going to do in this experiment before we get started on the lecture. So what we have here are various lengths of columns, and they're all about the same diameter, and they're hollow. So, what you do is you would take your column, you would measure it for the length and the inside and outside diameter, and then you would take your column and you would set it up on these fixtures that we have at each of the lab stations. So in this case we have a fixed pin setup. Each station would have a different setup, so one would be fixed pin, another would be pin fix, then we have fix fix, and then we have pin pin. So then you would go ahead and you would get your column, and again you would set it up to the fixture. So in this case it looks like we have a fixed pin and we have a short column here. Okay, and then here we have a dial gauge. So what this would do is it would measure the deflection that we're going to have on this column. So once we start applying this compressive load, each of these columns, they're going to deflect outwards. And this dial gauge would be used to measure that deflection. What I found in the past experiment when I did this last semester, it's really inconsistent, especially on these short columns, to measure that deflection. So if we were going to actually do this experiment, I may or may not have you measure the deflection. And instead, we would just measure the critical load of this column. The critical load is going to be the point where your column is kind of the last point where it's neutrally stable. And then once you go past that critical load, you're going to have failure, whether that's in the form of crushing for a short column or buckling for a long column. So in this case, we have a long column set up here, and then, as you would expect, this long column right here, that's going to buckle. And this is what it's going to look like. So these long columns, they deflect quite a bit, especially compared to the short column. So anyways, this is what the experiment would look like if we could do it. Unfortunately, that's not looking like it's going to be the case, but I want to give you an idea of what it would look like and what we're kind of doing here in the lab. Okay, so now we'll go ahead and we'll get started on the lecture. Okay, so the goals for the experiment, we want to look at short columns and study the crushing behavior that they have. And then we also want to look at long columns and look at the buckling behavior that they're going to have. And then for all of the columns that we have, we're going to take a look at the critical loading for each column. Okay, so the first thing we'll talk about is stability. Okay, so what I've written out here is that an object under tension can be statically stable because the tensile forces align the member along the axis of loading. Okay, so for us, we saw this in our first two labs. We had our objects under tension, and they were statically stable. So there wasn't any flexure, basically, when we were loading these objects in tension. Because this tensile force, it aligned along the longitudinal axis of our member. So it was stable the whole time until we had our fracture because of the necking. In this case, for compressive loading, a member can be statically unstable if there's misalignment of our compressive forces or if there's a lack of uniformity in the member. So, you can think of it like if you have one of those kind of big erasers. Once you take that and you start compressing it along the longitudinal axis of that member, you're pushing it down, you're applying that compressive force, but you know from experience that at a certain force, that eraser, it's going to start to bend and it's going to be unstable. So think about it this way, right? That's kind of some experience that you can draw on. So a lot of the times when we have these compressive forces, they end up bending or buckling, which is what we're going to see in this lab. Okay, so now let's define what a column is. Okay, so a column is going to be a long, straight prismatic bar that's subjected to compressive axial load. So you maybe didn't really need this formal definition. You already kind of know intuitively what a column is just from your everyday life. And then as we've kind of hinted at before, buckling is going to be a sudden large deformation due to a slight increase of a load when our structure had shown little, if any, deformation before the load increased. So again, I want you to think about that eraser that we just talked about. We're applying a load to this eraser, a compressive load, and there's little or no deformation as we're applying this load. But at a certain point, as we continue to increase this compressive load, then now we have this large deformation that you see in the form of basically buckling for that eraser. Okay, so now we're going to discuss equilibrium. So again, we're going to stay in this kind of topic of stability for a column, as this is a really important theoretical concept for this. Okay, so what I have here is equilibrium. So at the critical load, our column is it's in neutral equilibrium. So let's think of it this way. Once we're applying our compressive load, during this time the column is going to be stable. Once we reach this critical load, then we're going to be in neutral equilibrium, as I said. And once we go past this point, then we're no longer going to be stable. So we'll go back to the eraser. As we're first applying our load, we're stable, and then we're going to reach this critical load where we're at neutral equilibrium. And at this critical load, once we go right past that with a little more increase in load, then we're no longer going to be stable and we're going to have this buckling occur. Okay, so kind of a conceptual picture here. This first picture that I have, this is a stable system. So I've drawn out these kind of balls, I guess. So let's say that we're starting here in the center. We're starting right here. And then if I was going to apply some kind of force on this ball to move it, it could go to the left or to the right, but either way it's going to go up this kind of slope here and it's going to come back down to the center. So it's going to be stable. In this second picture, I have an unstable system. So again, if I was going to start in the middle, if I applied a load to the left or to the right, this ball, it's going to fall off our slope here. So we have an unstable system. And then the last one here is neutral equilibrium. Okay, so here if I was going to apply force to the left or to the right, it's going to move over a certain amount of distance. We'll just call it delta x. Okay, and in this case, it's not going to fall off our slope here. It's going to just, it's going to move left or right a certain amount of distance. So while we're not necessarily stable, the ball has not gone back to its original position, we're also not unstable. So at this point, this neutral equilibrium, keep in mind that this is at the critical load of the system. But once we go past this critical load, then we're going to be unstable and we're going to have this buckling occur. Or failure, depending on the column. Like a short column, that's not going to buckle much. It's going to fail in a different way. It's going to fail by yielding, which we'll talk about a bit later on. Okay, so far throughout this lecture, we've been talking about the critical load fairly often, so hopefully you have kind of an idea of what this is like. But again, it's the maximum compressive load for which a column is going to be in stable equilibrium. So one of the things we want to do in this experiment is find the critical load and the critical stress of each column that we're going to test. So to do that, we're going to need some equations, obviously. So we'll go ahead and we'll write this first one down. It's going to be called the Euler buckling load. Okay, so I've written this out as PCR, where PCR is the buckling load or the critical load, is equal to pi squared times the elastic modulus times the moment of inertia divided by the length squared. Okay, so this is going to be our theoretical equation for the critical load. And then another thing that we should note here is that this equation is only going to work well for long columns for which our slenderness ratio is large. So I've said two things here that I haven't defined so far. I've said that this is only going to agree for a long column. Well, that's pretty vague. I don't know what a long column is versus a short or an intermediate column. So we're going to go ahead and we'll define this. And then I've also said for which the slenderness ratio is large. So again, I haven't defined what this ratio is, so we're going to build up to this as well. So if we look at this equation that we have for Euler buckling, we can see that we can increase our stability in a few ways. So basically what I mean by this is if I change some properties, I can increase what the Euler buckling load is going to be, and that's going to mean that we're going to be more stable. So the first thing we can do is increase the stiffness of our column, so we can use a different material basically. The second thing we can do is decrease the length of the column. This one is not as practical in real life situations. If you need a column that has to be a certain length, well, you can't just say, yeah, I'm going to make this shorter, so this one isn't as practical. And then the third one is going to be to alter the geometry. So what I mean by this is basically change the geometry to change our moment of inertia so we can increase the moment of inertia and thus increase the critical load and thus increase the stability of our column. Okay, so now I've written out the critical stress, which is another thing that we want to know for the system. So the critical stress is just going to be the load over the cross-sectional area. So plugging in for our critical load and our cross-sectional area, we can get to our equation that I have on the bottom here. So the critical stress is going to be equal to pi squared times E divided by L over K squared. So this L over K, this is going to be an important property for us. It's going to be called the slenderness ratio. So L is the length of the column, and K, this is another property that's going to be called our radius of gyration, and that's going to be equal to the square root of the moment of inertia divided by the cross-sectional area. Okay, so the radius of gyration, this is basically a geometric property for our column. Okay, so let's write out a few things here. We now know that L over K, that's going to be called the slenderness ratio. And basically this is going to help us define what a short column is, what an intermediate column is, and what a long column is. And then one more thing that we're going to note here is that Euler buckling is an elastic phenomenon. So the critical stress is going to be below the proportional limit. So basically if we apply a load and we reach this critical load, I can still take off this load and we can recover all of this deformation that we just had. It's if I go past this critical load, then we're no longer going to be elastic. Okay, so our slenderness ratio, L over K, this is going to again define whether a column is short, intermediate, or long. So remember for our Euler buckling load, I said that this is only going to apply for a long column, and I was kind of vague as to what a long column was. Well, as it turns out, L over K, this ratio is going to tell us if our column is long or not. So what if we don't have a long column? How are we going to find this critical load? If it's short or if it's intermediate? So for that, we're going to develop how to do that later on in this lecture, but just keep in mind that this equation here for the Euler buckling load, this is only applicable to a long column depending on our slenderness ratio. Okay, so this is going to define our short, intermediate, and long columns. So if our slenderness ratio is less than 49.67, it's going to be a short column. If it's in between 49.67 to 63, it's going to be intermediate. And if it's greater than 63, it's going to be long. So in the beginning of this lecture, I showed you different end conditions that we had. I showed that we had a pin-pin, a fixed pin, and fixed. This was for the actual lab setup. So our assumption earlier on with the Euler buckling load, that assumed we had a pin-pin fixture. But as we know, we can have these different setups as well. And as it turns out that these different end conditions, they're going to have a significant effect on when we reach this critical load, and once we go past that load when our buckling occurs. So we need a way to incorporate these different end conditions and still be able to find what our buckling load is going to be. So in this case, we're going to introduce a concept called effective length. Okay, so the effective length, LE, this is going to be the length of any equivalent pin-ended column to have the same critical buckling load as the actual pin-pin column. Okay, so we're going to have some ratio basically of our length here for this equivalent length, where we can say basically if we have like a fixed column, we're going to have some equivalent length to then match the critical load that the actual pin-pin column has. So hopefully that kind of makes some sense here. And then take note that for a pin-pin column, because we derived our theory off of a pin-pin column, that effective length is just going to be the length of the column. So I'm going to draw a few different fixtures that we have here. So the first one will be for fix. Okay, so I've drawn out these different fixtures. So we have fix, pin fix, and free fix. So fix, that effective length is going to be 0.5 times the length of our column. And then what we're going to do is we're going to use this effective length in our calculations later on. Then for pin fix, the effective length is going to be 0.7 times the length of the column. And then we have free fix, where the effective length is 2 times the length of the column. Now for this, I put a star on because we're not going to use this loading in the lab, so it's just kind of for your general knowledge, but you don't need to know it for the lab. Okay, so now as I said, we're going to take our effective length idea and we're going to incorporate that in basically all of the equations that we had earlier on. Okay, so I'm going to go ahead and do that now. Okay, so now I've just rewritten the equations that we had earlier to incorporate this effective length concept. So we have the critical load, then the critical stress, and then our slenderness ratios for short, intermediate, and long. So again, all I've done here is I've changed L, which was assuming a pin-pin column, to LE to incorporate our concept of effective length. Okay, so as we said before, the Euler buckling equation doesn't explain how short and intermediate columns fail. So we can't use that equation that we had from before. So what we have here is for short columns, they're going to fail basically with our yield stress. And so that means that they're going to fail before stability failure. So let's write this out. Okay, so this is saying that our critical stress is equal to the yield stress, and this is going to be before stability failure. Okay, so before stability failure means that it's basically not going to have this big buckling load. It's mainly going to crush, as you can see in my amazing drawing that I have on the right. So what I have here is our column before the critical load is reached, and then we reach our critical load, we go past that, and then this column is going to crush. Okay, and then for intermediate columns, for this we're going to use empirical formulas, and for this it's going to be a combination of kind of crushing a little bit and buckling, as we see in the long column. Okay, and then as we have noted throughout this lecture, for the long columns we're just going to use the Euler buckling equation that we've developed. Okay, so now I've drawn out this kind of graph here in this plot. So this is going to show us basically the range where each of these columns are going to fail. So here I have the, on the horizontal axis, I have the slenderness ratio. Then on the y-axis, I have the critical stress. And then you see that my plot here is starting out at the yield stress. So what this should hopefully indicate to you is that in this range, this is when the short column is going to fail. Okay, so we have short columns right there. And then our critical stress is going to decrease. So what this should imply to you is that our column is starting to get longer, and that it's going to fail at a stress that's not as high as a short column would. So in this middle part, we have intermediate columns. Okay, and then once we continue to decrease our critical stress, and we're increasing our slenderness ratio, we're going to have the long columns here at the end. Okay, and then basically what we also have is a plot here, a different plot that's going to be the experimental plot. Okay, so where I've indicated short, intermediate, and long along the black plot, that's going to be calculations that we have from theory. So what you'll do is basically look at what the yield stress is for the material that we're going to use in the lab. That'll then tell you when our short columns are going to fail. And then you're going to use the empirical formula that we have for the intermediate column. Then you'll get when those fail. And these are all, again, we're going to be increasing this slenderness ratio throughout. And then you're going to use the Euler-Buckling equation for the long columns. And then you're going to have experimental data from the lab. And basically you're going to plot that, and we're going to have two plots on this one graph to compare the theoretical plot to the experimental plot. Okay, so again for short columns we have a yield stress, that's when it's going to fail. And so I think we're using aluminum. This is what I have on my deliverables handout that I'll upload for you guys. So this yield stress should be around 40,000 psi, but you should double check this on your own to be sure that's correct. Then for intermediate columns, we're going to use an empirical equation. So this is given from the manufacturer for these columns basically. So we have this equation as 38,300 minus 202 multiplied by our slenderness ratio, and that's going to give us the critical stress where the column is going to fail after that. And then for long columns, again, we're going to use the Euler-Buckling equation that we developed earlier on in this lab. Okay, and then the last thing that we're going to do for the experiment is you're going to plot the deflection versus the load. And you're going to do this for all 12 specimens as well. That's what we're going to have in the lab. Okay, so you're going to have your graph here. Okay, so we're going to have our deflection, delta. Then we're going to have our load, P. And then you should see some kind of graph that looks like this. So basically as we increase the load, we're going to increase the deflection. Then we're going to reach our critical load, at which point our deflection is going to kind of even out here at the top. We're not going to be able to have any more deflection because we've reached that critical load and we've now buckled for the column. Okay, so you're going to be doing that for the experiment. Okay, so a few more things that I'll note. I'm looking at my notes right now. So we are using aluminum 6061T6 for the experiment. And then I'll just write out a few more equations that you might want to take note of for your calculations. Okay, so the radius of gyration is the square root of the moment of inertia divided by the cross-sectional area. And then the moment of inertia for our rods that we're using, they're going to be equal to pi divided by 64 multiplied by the outside diameter to the fourth minus the inside diameter to the fourth. Okay, and then our cross-sectional area is going to be pi over 4 multiplied by the outside diameter squared minus the inside diameter squared. And then lastly, we're going to have the radius of gyration. I probably should have put this up top, but whatever. We're going to write this out now, plugging in for our moment of inertia in the cross-sectional area. And that is equal to 1/4 multiplied by the square root of the outside diameter squared plus the inside diameter squared. Okay, so hopefully these equations, they're going to help you out. They're also going to be on your deliverables handout. I'm looking at that now. And I should have all of the relevant equations that you need on the handout to make it a bit easier for you. Okay, and then I'll note one more thing. Although we're not doing the experiment, it's good to know. If we were doing it, we would increase the load increments for the short columns by 75 pounds, and then for intermediate columns by 50 pounds, and then for long columns by 10 pounds. Okay, so we're doing that so we have a good amount of data for each column, but as you should know now from this lecture, the long columns, they're going to fail pretty fast compared to the short columns, so that's why we're doing it up to increments of 10 pounds. Okay, so that should be all of the theory that you need for this experiment. If you have any questions, feel free to email me, and I'll get back to you as soon as I can. So, hopefully you've enjoyed this lecture, and unfortunately it's looking like we're not going to be able to do the lab, but we're going to continue on. Okay, so I'll see you for the next lecture.